Check. Okay, so before the break, we started looking at gradient descent algorithm and how to improve it, right? Like, so we looked at a bunch of challenges, like with the standard gradient descent algorithm, like so, which includes how to tune your learning rate, like so, like what's the ideal learning rate, like, and how to tune your learning rate schedule, right? Like, and also like this fact that we are actually using one learning rate for all the parameters, maybe it doesn't make sense, right? Like, so we want some sort of adaptive learning rate for each parameter or each layer, right? Okay, so I was about to start here, right? So basically we're going to look at different ways to improve the gradient descent algorithm. And they can be broadly classified into two families of algorithms. Okay, so one is based on this idea of momentum. Okay, so the second family is basically methods which do adaptive learning rates. Is it clear? Okay, so now first let's start with the idea of momentum. Okay, so momentum is typically used to accelerate the convergence of gradient descent. Okay, so can we speed up the training process? Can we speed up the convergence of gradient descent, like by doing something to the update, right? Like that is what the momentum is about. It's about accelerating the convergence of gradient descent. Okay, now this is inspired from momentum in physics, right? Like, so let's say like an easy way to understand how this works is imagine you're dropping a ball from the top of this hill. Okay, so when you drop this ball, it's going to start rolling, right? As it rolls down, it will gain some momentum, which means it's going to roll faster and faster, right? So as it rolls, it's going to roll much faster and reach the bottom. Well, if it rolls too fast, it might even overshoot, right? Like we need to be careful about that part. Is that clear? So the original gradient descent intuition, like so we talked about how if you are blindfolded and standing on the top of the mountain, you take tiny steps to go down, right? Like, so now imagine instead of being blindfolded, like your eyes are open and you're running, right? Like so you're going to gain momentum as you go down the hill, right? Like so that is exactly what momentum is going to do. Is that clear? Now let's see how to implement this, right? Like so we're going to see like a couple of ways to do momentum implementation. The first is this idea of SGD with momentum, SGDM. Okay. So this is what we're going to do. Like, so we're going to integrate the gradients that we are getting over time. Okay. And we're going to use this integrated gradient for updates. So instead of updating with just my current gradient, I'm keeping a running average of all my gradients. Is that clear? So let's call that term VT. Okay, so VT is gamma times VT minus 1 plus alpha times the gradient. Now I'm going to do theta is equal to theta minus VT. Is it clear? So this gamma that you see here is called momentum coefficient. Okay, so typically we would set it to 0.9 or 0.9, like something that is close to 1. This is the hyperparameter for SGDM. So now SGDM has two hyperparameters. There is learning rate alpha, but also the momentum coefficient gamma. Is that clear? Any question? Now what happens is you're kind of integrating all the gradients, right? Like so if you're getting tiny gradients but consistent gradients, then it's going to add up, and your updates are going to be larger. Is that clear? However, if you're getting conflicting gradients in a direction, right? When you integrate these conflicting gradients, it's going to cancel and make the process of like convergence smoother. Is that clear? So the best example is like something like this, like where like you have two directions, right? Like so the x-axis direction is like when you're moving with gradient descent, like you're going to have this zigzag effect. Okay, so you want to reach here, right? And gradient descent is going to do something like this and eventually converge. Okay, so this is happening because the valley looks like this, right? So there's not a lot of space to move. Like any small change you do, like you're going to the other side, right? So you're just crossing the valley for every step. Okay, now one way to avoid this is if I know that once I'm taking positive direction, one's negative, one's positive, one's negative, right? I can cancel these things, smoothen the steps, right? Like and progress even faster. So that is what SGDM will do. So if you do SGDM here, it's going to take bigger steps towards the minimum. Is that clear? This is SGDM. Okay. Now, one of the problem with classical SGDM is, as you can see here, if you're moving too fast, right? Like as you gain more momentum, like you could even overshoot the minimum, right? Now, let's think about this from like a person running from up the hill, right? Like so, your behavior would be different when running from uphill, dependent on whether you're blindfolded or not, right? Like so, think about the situation where you're blindfolded, you're running downhill. Now you don't see the minimum, right? Like so, you don't see the bottom of the hill. So you would just continue accelerating because you don't know where to stop, right? On the other hand, imagine you're running downhill, but then you see the bottom. So what would you do? Like, so you are accelerating from the top, but then when you're closer to the bottom, you will decelerate, like because you know that you have to stop here, right? So you have to reduce your speed so that you stop in the right direction, right? Like so this extra sight, right? Like so like this extra like looking ahead is really useful, like when you're applying momentum. Okay, so this is what we are going to do in the second algorithm. So we are going to modify the momentum strategy, okay, and do a variant where we look ahead before taking steps. So this algorithm is called Nestro's accelerated gradient, NAG. Okay, Nestro is one of the pioneers in the field of optimization, and he has done a lot of foundational work in optimization. So this is Nestro's idea, like which is basically to look ahead before computing the gradient. Okay, so how does this work? Let's actually look at SGDM first. So SGDM, right? So you're here, okay? Your momentum, let's say your momentum looks like this, and your gradient looks like this. Okay, so this is my current gradient, and this is my momentum, right? Now, when you take a step using SGDM, it's going to take an average of these two things, right? Like so you're integrating the gradient with the momentum, so you would get something. This is going to be your actual step. Right? Now, here is the thing. even before computing the gradient, you already have the momentum information, right? Like, so you are storing the momentum at every time step, right? Like, so you already have the momentum information. So which means instead of computing gradient from here, I can compute the gradient from here because I know I'm going to take the step, right? So I can compute the gradient from here and use that gradient here. Okay, this is a really smart choice which helps you to look ahead and optimize. Okay, so the way in which NAG works is you are here and this is your momentum, right? Now instead of computing the gradient at the red point, I will compute my gradient here. This is my look ahead gradient. Okay, so then the actual step, this is going to be my actual step. Is that clear? Now, if I have to write an equation for this, right? Like, so Vt is going to be gamma times Vt minus 1 plus alpha times the gradient, but not at theta. It's actually at theta minus gamma times Vt minus 1. Okay, so then theta is equal to theta minus Vt. Is that clear? Any question? So you could either use SGDM or Nestros accelerated gradient, right? Like so, and both these methods are going to help you in speed up the convergence of your algorithm. Okay, so now let's look at the second class of optimization methods, which is to use the idea of adaptive learning rates. Okay, so here the idea is, can I adapt the learning rate for individual parameters so that we can optimize better? Okay, of course you can do layer-wise adaptation, but we are going to talk about single parameter adaptation. Like for every parameter, like I have a adaptive learning rate. Like what does this mean? This means if you have a million parameters, previously you had only one learning rate, right? For all the million parameters. But with this technique of adaptive learning rates, you can adapt the learning rate for all the million parameters individually. Is that clear? So if you have to do it naively, it's almost impossible, right? Like so if you have to do this naively, you have million hyperparameters to tune, right? So we don't want to do that. Like we want to keep the hyperparameter to be still just one, like the learning rate, right? Or close to one, like 2, 3 hyperparameters, but have this flexibility of adapting the learning rate for all the million parameters. Okay, so there are a bunch of algorithms which does this. Like so, probably the very first algorithm which this was called ADAGRAD. Okay, which stands for adaptive gradient. Okay, so the idea of ADAGRAD is to tune the learning rate depending on the magnitude of the gradient. Okay, if you have very small gradient, you want bigger learning rate. If you have very large gradient, you want smaller learning rate. It's a good heuristic, right? Like so, if a parameter gets a very small gradient, then to make progress, you need to increase the learning rate. Okay, if there's a parameter which is getting too big gradient, right? Then to stabilize the progress, like you need to reduce the learning rate. Okay, now let GTI be the gradient, okay, for the, okay, I don't know, a t time step for the ith parameter. Okay, I is the parameter that we are looking at, and t is the time step. Okay. Now, with this new notation, is GD equation can be written as theta t plus 1I is equal to theta ti minus alpha times GTI, right? So that is SGD. Now, the way in which undergrad is going to work is theta t plus 1I is equal to theta ti minus alpha divided by square root of summation p is equal to 1 to t gpi square plus some epsilon gti. Okay, so what am I doing here? Like I'm basically taking a root mean square of all the gradients. Okay, so I take all the gradients from first time step to the tth time step. I'm squaring them, summing them, and taking a square root. Right? This is just the root mean square of all the gradients. Just to make sure that this is not division by 0, like I add a small like epsilon here, which is 0.001 or 0.0001, like a very small value close to 0. Is that clear? Yeah. Well, in case this is 0, it helps with the numerical errors. Yeah. T is the iteration, I is the parameter. This is like the gradient for ith parameter of the tth step. So look at this denominator, right? Like so now let's say you have very large gradients. Now this value is going to be very large, right? So you're dividing the learning rate by a larger value. So the learning rate is going to shrink, right? Similarly, if you have very small gradients, then the root mean square of the gradients is going to be very small. You're dividing the learning rate by a smaller value, right? If it is less than 1, then the learning rate is significantly increased. Is that clear? Now, this is also true for sparse and frequent gradients. Like for example, whenever you get sparse gradients, right, your learning rate is going to be high. And whenever you have frequent gradients, and they're also large enough, right, then the learning rate is low. Is that clear? Now, this is the time step, and this is the parameter index. Any question? Yeah?
So like this whole thing is find the learning rate, which is going to be multiplied by the gradient. But
Yes.
and it's inversely the inversion that gradient point out just normalize the vector in the flow. There's maybe has like a desired it's not the direction of the vector is the type of that point.
So you mean just normalize the gradient? You can do that. Like so, it's called normalized gradient descent. Okay, so you can definitely do normalized gradient descent, but it is not going to work for every architecture. Okay, especially if you have recurrence in your architecture, it's not going to be very easy to do normalized gradient descent. But it is a valid method. Like so, you could do normalized gradient descent, and that would also resolve this vanishing gradient issue.
The learning rate
Just once.
multiplying it by the gradient. It's like
No, they are very different, right? Like so here you are they are different in the sense like here you are increasing or decreasing the learning rate depending on the root mean square of the gradients. But the normalized gradient descent doesn't have this memory. Like, so you're just using the current gradient, right? Like this has this aggregating effect. Okay. Now, are there any like potential like caveats with AdaGrad? Yeah. Yeah. So that's one of the issues, right? Like, so if you are randomly initializing and you're starting with some random function, right? So you might get large gradient in the beginning, right? So this large gradient is going to dominate this root mean square, and you're immediately reducing the learning rate size, like learning rate, right? Like so that is a potential issue. Any other issues? Any other issues? Yeah.
Because too big, the small, then it's very much as if we're back to the regular method. First it's big, I mean, just eventually the averages become.
No, it's going to be even worse than the regular method. Okay. So that's the second. Okay. The second issue is this is sum of square of the gradients, right? The square of the gradient is always positive. So as you sum this over 10 steps versus 100 steps versus 1,000 steps, right? It's going to keep growing. So which means AdaGrad would actually stop learning at some point. Okay, the problem with this formulation is because the denominator is strictly increasing, over time, the learning rate is going to go close to zero, and at some point it will become almost zero. Right? So which means even though the model has not converged, the learning process is not progressing. Like, so it's just stopped because of this nature of AdaGrad. Okay? Now, how can we fix this? Yeah. You can reset this every 10 iteration. Okay, any other thoughts? Yeah.
Divide the radius sum by Q and add them to the next one. So like on average, the last one.
Somehow reduce the significance of the past. Yes. Any other thoughts? Why would regularization help? You're already not learning. So what's the goal here? The goal is to somehow forget the past, right? So like these are all valid approaches. You either reset at some point, right? Then it's kind of annoying heuristic because you need to decide when to reset. Is 10 step a good idea, 100 step a good idea, right? So like a more elegant solution for this is to have some sort of running average, okay, with some recency bias, okay? So this is what RMS prop does. Okay, so RMS prop is another adaptive gradient method, okay, which basically maintains the statistics, the gradient square statistics, the EG square of t, which is given by rho times EG square t minus 1 plus 1 minus rho times GT square. So what is this doing? Like, so instead of taking sum of all the GT squares, I'm doing rho times the previous sum plus 1 minus rho times the current GT square. Yeah. Oh, it's rho, like, so it's a hyperparameter. So this is called a decay constant. This is also typically set to 0.9 or close to that value. Okay. Now, the RMS of G is given as square root of E of G square T plus epsilon, and theta T plus 1 is equal to theta T minus alpha by root mean square t times gt. Is that clear? Yeah. Yes. Well, if rho is 1, if rho is 0, then you are only considering the current. There is no, like, yes, there is no past, right? Like, so when rho is 1, then you're considering the past, like you're setting it to 0.9 so that like there is some sort of exponential reduction in the importance for the past. Is that clear? Any question? Now, as a summary, right? Like, so we have gradient descent, and there are two ways to improve gradient descent. Like, you can either do momentum based methods or adaptive learning rate methods, right? Now, with momentum based methods, like you could either do SGDM or NAG. With adaptive learning rate, you can do AdaGrad, RMS prop, right? Now, one thing I want to highlight is I picked these two representative algorithms, but then there are hundreds of variants of momentum methods. Okay, and the same is true for adaptive learning rate. Maybe there are thousands of variants of adaptive learning rate methods. Like so, like the whole field of optimization, at least deep learning optimization right now, is about coming up with better like methods for training neural networks, like which includes better momentum methods, better adaptive learning rate methods. Is it clear? Now, yeah. We'll talk about it. Okay. So now, before answering the question, like one thing I want you to note is these are two complementary methods, right? So they serve different purposes. So momentum is about accelerating the convergence, right? Now, adaptive learning rate is about changing the learning rate. So in theory, you could combine momentum-based methods and adaptive learning rate methods, right? Okay, so can you please not talk in between? Okay, so in theory, you could combine momentum-based methods and adaptive learning rate methods, right? Like so one popular such one such popular combination is ADAM, okay, which stands for adaptive moment estimation. Okay, so ADAM uses both the ideas, yeah?
Is the RMS prop strictly better than AdaGrad?
I would guess so. I'm not sure if we can prove that, but intuitively, yes, right? Like so, because AdaGrad is going to stop learning at some point. RMS prop would not. Okay, well, maybe a quick anecdote about AdaGrad. Okay, so AdaGrad is one of the like examples of like how theory could benefit practice. Okay, so AdaGrad was originally proposed by the theory community. Like so, this was a Colt paper, I guess. Like so, Colt is Conference on Learning Theory, which is too far from machine learning conferences in terms of the practical applicability of things that are being discussed there. Okay, but this is such a great example because it really created this whole field of adaptive learning rate optimization methods for neural networks. And without AdaGrad, I don't think we would be training neural networks like at scale. Okay, well, even though we don't use AdaGrad for training, like we use RMS prop or ADAM, right? All these methods were built on the top of AdaGrad or inspired from AdaGrad. Okay, this is one of the few algorithms that came from theory to the applied machine learning. Like the other examples are SVM and boosting. So boosting also came from the learning theory community to the practical machine learning community. Okay, so in that sense, AdaGrad is an important algorithm to know about. Okay. Okay. Now let's talk about Adam. Adam is basically a combination of RMS prop and momentum. Okay. So when you combine momentum with RMS prop, you get Adam. So which means you have both MT and VT vectors. MT is basically beta 1 times MT minus 1 plus 1 minus beta 1 times GT. And VT is beta 2 times VT minus 1 plus 1 minus beta 2 times GT squared. So that is first order information. Then you have the second order information, right? Like, so you're integrating both the first order and second order statistics, like the GT and GT square. Okay. Now you could do theta t plus 1 is equal to theta t minus alpha by Vt plus epsilon times mt. Okay. So here you see the momentum effect, right? Like, so you're integrating gradients in MT, so that is your momentum. Then you're also dividing by VT, which is basically the root mean square of the gradients. Is that clear? So you're essentially combining RMS prop and SGDM. Yeah. This the gradient square. Yes. Right. Now there is some sort of initial bias in estimating MT and VT because we set the M0 and V0 to be all 0. Okay, like the model is kind of biased towards the 0 vector. So the original Adam paper did some sort of bias correction. Okay, so how is bias correction done? Like, so MT hat is equal to MT by 1 minus B1 T, sorry, or T. VT hat is VT by 1 minus B2 T. And you use, and you use V hat and M hat here. Is that clear? Any question? Now, Adam is probably the most popular optimization method. Like, not exactly Adam, but some variant of Adam. Like, so Adam W, which is basically Adam plus L2 regularization added as a weight decay term. Okay, so Adam or Adam W is probably the most popular optimization method for neural networks right now. Okay, so you would see almost every machine learning paper using Adam W for training their model, or Adam or Adam W. Okay, so some version of Adam, right? And there are also thousands of papers written on coming up with an alternative for Adam, like including a bunch written by my students, like where we are, like, this is one of the active research directions in my lab, like where we are trying to come up with better optimization algorithm than Adam. But one thing I want to highlight is it's extremely difficult to replace Adam as the popular optimization method, okay? Simply because in the last 10 years, like after the introduction of Adam, like almost every deep learning research happens with Adam. So in some sense, the research evolved with Adam, right? So any idea that worked with Adam as an optimization algorithm got picked up. Any idea that did not work with Adam, people just threw away that idea while doing research, right? So this is kind of a weird side effect of everybody using one optimization method. So my general advice for you, like if you're serious about doing machine learning as a researcher, right, is not to get into this trap of trying ideas with just Adam. Okay, so in general, whenever you start a new project, yes, do Adam, but try at least 3 different optimization methods. Okay, so like which are SGDM, RMS prop, and Adam. okay, and try a few learning rate, like different step sizes for all these methods, right? Like, so now these are the popular methods, but as I said, there's a lot of research happening on improving these methods, right? But there is also a lot of research happening on improving the second order optimization methods. Like if you remember, we looked at Newton-Raphson, right? Like, so Newton's method is what we call the second order optimization methods, right? So can someone tell me the difference between first order and second order optimization methods? Yeah. In theory, yes, but in practice, we will still use learning rate. So what's the major difference between the first order optimization method and second order optimization? Like what kind of extra information the second order method has? Yeah. Yes, you have the Hessian, which gives the curvature information, right? So the second order methods exploit the curvature information to have better steps, right? While the first order methods don't have the curvature information, okay? So in that sense, for a long time, people working with second order optimization methods argue that they are strictly superior to first order optimization methods, right? Like, however, the main challenge with second order optimization methods is they're computationally very expensive, right? So, which means this is another active research area. There is a lot of work in the literature on coming up with scalable approximations for the Hessian. So instead of computing the actual Hessian, can we approximate it in such a way that the computation is cheaper? And even though it is not going to match the Adam or SGDM level computation, if it is 2 times, 3 times larger, that's okay, right? Like, it's not okay if it is 200 times larger. If the computation is 200x, then you're going to be 200x slow, right? Nobody would use this algorithm, right? Like there are a lot of interesting algorithms that are being developed in the last few years, like which basically tries to approximate Hessian in smart ways. Okay, so like some of the notable methods are things like shampoo, muon. Okay, so these are methods which approximate the second order computation to the extent that serious second order optimization method researchers don't consider these to be second order optimization methods. Okay, like, so sometimes people think these are still first order optimization methods. Again, this debate is true even for Adam. Like, so you could consider methods like Adam and RMS prop as already doing some second order thing. Okay, like if you go back to the RMS prop equation, right? So you see you're using the root mean square of the gradient here, right? So the root mean square of the gradient, which is basically g square, can be considered as a diagonal approximation of an Hessian. Okay, so in some sense, this is already an approximation of Hessian. So you could argue that RMS prop and Adam are already approximations of second order methods, right? Like, I would put them as like something like 1.5 order methods. Okay, like it's because it's neither first order nor second order. It's neither first order in the sense it's not just using the gradient, it's using some sort of GT square as well, right? Like, so, like, which is an approximation for the Hessian. Is that clear? Any question so far? Now, if you use modern machine learning frameworks like PyTorch or JAX, almost all these optimization methods are implemented for you. So if you want to gain more intuition on how to train neural networks, I highly recommend that you pick a simple MLP, okay, like with MNIST or whatever, right? Like, and change the optimizer. Okay, like try training this with SGD, try training this with SGDM, try training this with Adam, right? Like, so you have to get some sort of hands-on experience in doing this to understand how the optimizers work. And also the best way to gain intuition for the hyperparameters of these optimizers, like for example, what is the importance of rho? What is the importance of gamma? What's the importance of epsilon, right? Like, so like when we introduce epsilon, like I often say, oh, this is just to avoid division by zero, right? But epsilon actually does more than avoiding division by zero, okay? Like it really becomes crucial, like in the optimization, like the value of epsilon could speed up or slow down the optimization, okay? So these kind of things you will learn if you try running different values of epsilon, different values of gamma, different values of rho, etc. Okay, and you have to do this for a bunch of models, a bunch of data sets, so that you get a better sense of these hyperparameters. Is that clear? So that would make a huge difference in your understanding of how to train neural networks. And right now, if you know how to train state-of-the-art neural networks, that's $1 million job. Okay, like I'm not joking. Like, so if people get even 10 million, 100 million, like if they know how to train very large models, and that requires a very strong hold in optimization as well. Like, so you should know how these methods work. Like, that's the first step, really. Is that clear? Any questions so far? Okay, I think that concludes our discussion on optimization methods. Okay, now